There's something a toddler can do without even thinking. But for decades, it was one of the biggest challenges in all of computer science. And that's simply looking at the world and, well, actually understanding what it's seeing.
Okay, so take a look at this. You and I, we know exactly what this is, right? It's instant, we see the spots, that classic cat-like shape, the powerful build, and our brain just goes leopard. Easy. But for a computer, this is just a giant grid of colored pixels. Millions of them. It has no idea what it's looking at.
So how in the world does a computer learn that this is a leopard and not, say, a jaguar or a cheetah or even just a big house cat? For years, this was the grand challenge. Trying to teach a machine to tell the difference between thousands of objects with any kind of real accuracy, it felt, well, almost impossible. Because the real world is just messy, It's so varied. And that leads us right into the heart of the vision problem. I mean, think about it. Recognizing an object isn't as simple as it sounds. A computer has to know it's a leopard from any angle, in bright sunlight or in shadow, even if it's partly hidden behind a bush or curled up in a weird pose. This was this giant wall of complexity that researchers just kept smashing into over and over again. So, to break through that wall, it became clear that the field needed three things. And the authors of the paper we're going to dive into today laid it out perfectly. First, you needed way, way bigger data sets, just more stuff to learn from. Second, you needed more powerful models to actually process all that data. And third, you needed better training techniques, smarter ways to teach these models so they wouldn't just, memorize the pictures like flashcards. And that first piece of the puzzle, it dropped in 2009, and it was a game changer. It was called ImageNet. And when I say it was a massive data set, I mean it was enormous. Over 15 million high-res images, all carefully labeled by people, covering thousands of categories. This was it. This was the giant digital playground that AI researchers had only dreamed about. So with this amazing data set, a new tradition started, an annual competition. You can basically think of it as the Olympics of computer vision. Every year, the best teams on the planet would bring their latest and greatest AI models to see whose could identify the most images from ImageNet. And in 2012, well, something happened that no one saw coming. Now, just to set the scene for you, the reigning champ from the year before had an error rate of 26.2%. That means the best system in the world was still getting it wrong more than a quarter of the time. Progress was slow, like really slow. If a team improved by 1 or 2%, that was a huge victory. And then this small team from the University of Toronto shows up. We're talking about Alex Krzyzewski, Ilya Sitskover, and the legendary Geoffrey Hinton. And they'd built something totally different, a massive deep neural network. I mean, way bigger and with more layers than anyone had ever really tried before. They called it AlexNet. And yeah, the entire field was about to get flipped on its head. So they reveal their results, and their error rate, it wasn't just a little bit better. It was 15.3%. Think about that. They didn't just inch ahead by 1 or 2%. They slashed the error rate by over 10 points in 1 year. This was it was completely unheard of. And this chart really puts it into perspective, doesn't it? Look at the gap. This wasn't just a win, it was a total demolition. AlexNet didn't just outperform the second-place entry, it made everything that came before it look like it was from a different century. This was the moment. The era of deep learning had officially begun. Okay, so the big question is, how? How did they pull this off? What was their secret sauce? Well, as it turns out, it wasn't just one magic bullet. It was a really smart combination of a few key ingredients. All right, ingredient number 1, speed. A network this huge should have taken an eternity to train, but the team used a new, much faster type of artificial neuron. It's called a Rectified Linear Unit, or ReLU for short. You can basically think of it as a super simple on-off switch. This tiny change made the math so much faster, and honestly, it's what made the whole project even possible. And you can see the difference right here. The solid line, that's the new neuron, just rocketing upwards. It learned 6 times faster than the old way, the dashed line. So a training run that would have taken a month, they could now do it in just a few days. That speed up was absolutely crucial. Okay, ingredient number 2. So even with ImageNet's millions of pictures, their model was so huge that it was at risk of overfitting, basically just memorizing the training images instead of learning. So what did they do? They came up with a clever way to get more data for free. They basically taught the computer to create variations of the existing images, flipping them, randomly cropping them, messing with the color balance. A brilliant hack. And the third ingredient is my favorite. It's a technique called dropout, and it is just so clever. Imagine you're a basketball coach, but during practice, for every single drill, you randomly make half your players sit on the bench. What happens? The players on the court can't just pass to the star player every time. They're forced to get better themselves, to become more resilient. That is exactly what dropout does to a neural network. It randomly turns off neurons during training, forcing the network to build stronger, more robust connections. And the final piece of the puzzle was the hardware. What powered this whole beast? Not some custom-built supercomputer. They ran the whole thing on 2 powerful, off-the-shelf gaming GPUs. It was a bit of a novel approach at the time, but it turned out that the kind of math GPUs do for video games is perfect for the kind of parallel number crunching that neural networks need. So, after all that, what did the network actually learn? Well, take a look at this. This is incredible. These are visualizations of what the very first layer of neurons taught itself to look for. No one told it to do this. It just figured out, from looking at millions of pictures, that the most important building blocks of vision are things like edges and textures and patches of color. But this is where it gets truly mind-blowing. The picture on the left, that's a test image the network has never seen. The pictures on the right, that's what the network thinks are the most similar images from its memory. And notice what it's doing. It's not just matching pixels or colors. It's matching the concept. It sees an elephant in a certain pose, and it finds other elephants in similar poses. It was actually learning to understand the meaning of an image. So let's zoom out for a second, because the impact of this one paper is, well, it's hard to overstate. This wasn't just about winning a competition. This was a fundamental shift for the entire field of AI. And the authors themselves say it right in the paper. They wrote, and I'm quoting here, "The depth really is important for achieving our results." It wasn't about one clever trick. The secret, the real breakthrough, was realizing that the size and depth of the network were key. Going bigger was, in fact, better. And that's the main takeaway. AlexNet gave everyone the blueprint. It was this massive proof of concept that basically shouted to the entire research community, this is the way. The recipe was clear: get a giant data set, build a really deep neural network, throw a bunch of GPUs at it, and use clever tricks like dropout to make it all work. And you can draw a straight line from that blueprint to literally everything happening in AI today. I mean, just 3 years later, in 2015, AI officially became better than humans at that same ImageNet challenge. A few years after that, the descendants of AlexNet were powering things like self-driving cars and helping doctors spot diseases. And today, the generative AI that's creating incredible art and writing code, it's all built on that same fundamental idea. This paper wasn't just a step forward. It was the starting gun for the AI revolution. Before 2012, you could argue that AI was kind of this niche academic field, making slow, steady progress. But after 2012, it became a full-blown engineering race, one that was set to change, well, everything. The question was no longer if computers could see. The question became, what do we show them next?